Okay, everyone. So today we're gonna start. We're gonna talk about applications of the second derivative, and so before we talk about the second derivative, let's have a look at the following graphs. These two graphs here. So what can we say about them? So the top, well, there's four graphs that you can see. So last time we talked about increasing and decreasing functions. So these top two functions are of course are increasing. So we have that these are increasing. And if you remember what that meant in terms of the derivative, it meant that the derivative is positive for this function. So f prime is positive, right? So for these two functions on the top, in the first row, we have that these functions are increasing, and that the bottom two functions are decreasing, right? So these are decreasing. Or which is the same as saying that the derivative is negative, right? So now let's have a look at the functions here in the first column, right? Well, they're these two. They're very they're both increasing, but they're increasing in different ways. So what you would say, it seems that the first one here, this one here, is increasing at a rate that is getting bigger and bigger. So they're increasing faster and faster. And this one is also increasing, but the rate at which it is increasing is slower and slower. So what do I mean by that? Let's actually draw the slopes of these functions at some point. For instance, the slope of this first function at that point would be, well, that's the tangent line, right? So the slope of that would be the derivative at that point. And if you take a later point here, for instance, let's take that point, then the slope would be this. And then if I take it even further, then the slope will be even steeper, right? So what does this tell me about this function? This is saying that the rate at which the function is increasing is getting bigger and bigger. So the rate, I will just write it down. So the derivative is getting bigger, right? Why is that? Because derivative is the slope at this point, and we see that the slope is becoming greater and greater. So that means the derivative is getting bigger and bigger, okay? So in this other example, the opposite is true. So we have, let's again look, take some points. So we have, say, this point here, and the slope is some number, and then here the slope is smaller, and here it's even smaller. So what's happening is, in this situation, the derivative is getting smaller, right? So geometrically also it's clear that even though both of these functions are both increasing, what we note is that this one here, geometrically, it's bending up, right? So because the derivative is getting bigger and bigger, for that reason we have that it's bending up while the other one is bending down, right? So that's why we give this a name, and we say that this function here is concave up, and this one here is concave down. So we can say also concave upwards or concave downwards. So what does it again mean concave up? It means that the curve, the graph of the function is bending up, and the other one means that it's bending down, right? And it really that has nothing to do this concave up or concave down concept. Doesn't have anything to do whether the function is increasing or decreasing. Well, the first ones we looked at, these both were increasing. So now we can look at these two examples where they are both decreasing. So let's see what happens to this one. So this one is decreasing, but is it kind of, am I trying to bend it up or bend it down? Well, I'm trying to bend it up, right? So if you want it more precisely, what we do, again, we can look at the derivative at this point. Well, it's a negative number at any point here because the slopes, it's a decreasing function, so the slope is always negative, but it becomes more and more positive. So what that means is that again, the slope is getting bigger and bigger. So this is again concave up. So I'm just going to write the derivative is getting bigger. So that means another way of saying is it is concave up. Okay, and this other situation we have that derivative here, see, it's a small number, it is negative, but it's becoming more and more negative, so it's going down at a faster speed, so that means it is becoming so the derivative here is getting smaller, which is the same thing as saying that the function is concave down. Okay, so we have now four functions here. So let's look at these ones here. So the top two ones, so the ones in this row are increasing, and the ones in this row they are decreasing. But these two in the first column are both what are they doing? They're bending up, right? So they're both concave up. And these ones here in the second column, they are both bending down. So that's what's called concave down. Okay. So concave down means bending down, and concave up means bend up. Okay. So here is the definition. We say that our function is the graph is concave up on an interval if the derivative is increasing, and the graph of f is concave down if derivative is decreasing, right? So the important thing here that not the function is increasing, but the derivative, right? So the derivative is increasing. If I said that the function is increasing, that would mean not concave up, it would mean that the function is increasing, it is just getting bigger and bigger. But in this case, the derivative is increasing. Okay, so so like if you want an example from real life, you have a car, you are driving, and if you're, say, driving away from home, then your distance is always getting bigger, but at some point you're accelerating. It means that the speed is getting bigger and bigger. So that's saying that your function is concave up, and at some places you press on the brake, so you're decelerating. So you're still going further and further from home, but at slower and slower speed. So that's concave down. Okay, so in this in the sense of the pictures, there is basically these four pictures that can happen. Okay, now so but what does the how can we do figure out if the function is in concave up or concave down using the derivatives? Well, we already know from last time that the function is increasing, and that's the same thing as saying that this first derivative is positive. So what about concave up or concave down? Well, concave up and concave down, you don't do that with the first derivative, you do it with the second derivative. So because what is concave up? It means that the derivative is increasing. So that means the derivative of the derivative is positive. So let me just write it. So this is saying that, so concave up means, let me just write it here. It means that the second derivative is positive. Okay, and concave down means that the second derivative is negative, right? So an easy way of figuring out whether the graph of a function is concave up or concave down is by looking at the second derivative and figuring out whether that's positive or negative. So using the second, let me just write it here. So if so the graph of f is concave up in the interval AB if the second derivative is positive, right? So the second derivative is positive in the same interval AB, and similarly f is concave down as the same thing as saying that the second derivative is negative. Okay, so that's how we figure out if the function is concave up or concave down. So in many situations we will have to find out the intervals where the function is concave up or concave down. Okay, so so now let's do an example. Let's do two examples. So here is the two examples. So determine the intervals where the graph of the function is concave up or concave down. So in this one here, so in the first one, so we have that f is concave up. So again, concave up, it means that it's bending up or the slope is becoming bigger and bigger. Well, from this picture, we see that this graph here is bending up in this interval and this interval here. So that's where the function is concave up. So that means I have to look at the interval from negative infinity to 1 and from 3 to infinity. So here in negative infinity to 1, and 3 to positive infinity, and f is concave down in this interval, in the other interval, right? So what's happening here? Here the function is concave down, meaning the derivative is becoming smaller and smaller. So let's look at the derivative here. So if I take a point here, it's some number, here it's smaller, here it's even smaller, and then it's becoming more and more negative. So it starts with being positive at this point here, and then it's becoming smaller and smaller and smaller. So that's what it means to be concave down. So it's concave down. So which interval is that? That's the interval from 1 to 3. Okay? So similarly in this example here, let's look at this. So where is the function concave up and where it is concave down? So let's see. So in this example, where is the function bending up? Well, it starts here, and see, it's kind of bending up, right? So until there. So here, if you take the derivative, then it's some big number here, then it's becoming smaller and smaller and smaller, and here it's some number which is not that big, right? So here we see that it is bending up, right? So it's concave up. So so this is, I should write that this is 0 here, right? So it's going to be concave up in this interval here, right? So in negative infinity to 0. Well, okay, so let's write also where it is concave down. Okay, so in this interval, see, from here to here, it's bending down, right? But then uh, it still continues to decrease, but now from this point on, it's bending up and then continues to bend up all the way here, right? So here is the only place where the graph is bending down, so that's where that's where it's concave down. Okay, so it's concave down in 0 to 1, and then from on this interval here, from 1 to 2, and then from 2 to infinity, it is concave up. So it's concave up all the way from 1 to infinity. Okay, so that's where this function concave up is concave up and concave down. So it's concave up in negative infinity to 0, and concave up again in 1 through infinity, and then it's concave down in this small interval here. Okay, so now the next problems are to find out where it's well, actually, here's another problem. So actually, before going there, let me remind you what this means in terms of the second derivative, right? So concave up in that interval also means that, well, that's the same thing where the function, the second derivative of that function is positive here, and also here the second derivative is negative, right? So wherever it's concave up, the second derivative is positive. Wherever it is concave down, it means the second derivative is negative. Okay, so next, let's do this problem here. So these are two functions. So the following graphs were used by some companies to illustrate what effect a projected promotional campaign would have on its deposits over the year. Okay, so the functions d1 and d2 give the projected amount of money on deposit with the bank over the next 12 months with and without the proposed promotional campaign. So the top one is the one which is with the promotional campaign, and the bottom one is without the promotional campaign. So what does this say? First of all, so we have to determine the signs of these derivatives. Okay, so let's do that. So let's say d1 prime t. Is it positive or negative? Well, d1 is the top graph, right? It's this graph here. Does it increase? Yes, it increases. Well, it means that the derivative is positive. That means the derivative is positive because the function is increasing. Similarly, the D2, well, it's not maybe clear, but it also is increasing, right? So these both functions are getting bigger and bigger and bigger, but the shape is quite different. This one is bending up, this one is bending down, even though not very fast. So they're both increasing. That means the derivative for both of these functions is positive, right? However, if I do the second derivative, well, the second derivative tells me whether the function is bending up or bending down. So let's see. D1 here, where is D1? D1, well, it does look like it's increasing faster and faster, and so it's bending up. So it means that the second derivative is positive. So I'm going to write it that the second derivative is positive. And for D2, well, look at this one here. It's getting bigger and bigger, but at a slower and slower rate. So it is bending down. So that means the second derivative is actually negative. Okay? So that's what we can say. And now let's see what we can conclude from this. Let's see. So it says, what can you conclude about the rate of change of the growth rate of the money with and without proposed promotional campaigns? So we want to say, what can we say about the rate of change of the rate? How fast? I mean, if it's both, they're both increasing, but which one's increasing at a faster speed, which space at a faster rate, and which one at a slower rate? Let's eliminate certain things from the beginning. So with the promotion, let's look at some of this one here. The first one says, with the promotion, the deposit will increase at an increasing rate, whereas the promotion, with the promotion, the deposit will increase at a decreasing rate. Okay, well, that's wrong, right? Because with a promotion, we saw with the promotion that they're increasing at a faster rate, and without a promotion, they're increasing at a slower rate. So if you look, so the correct answer, with the promotion, the deposit will increase at an increasing rate, and without the promotion, the deposit will increase at a decreasing rate. So this is my correct answer here. So the second one. Okay, so we have some other questions here. So it says the second one. The third one is, with the promotion, the deposits will increase at a steady rate. Well, what does steady rate mean? Steady rate means that the derivative or the rate is the same all the time. So it's basically a linear function. So none of this is a linear function. And the other one is saying with or without the promotion, deposits will increase at the same rate. So what that means is the graphs are the same, and they're clearly not the same. Okay, and they would be increasing. Okay, so this is this problem. Are there any questions about this problem? Okay, so the next ones. Okay, so now we're given functions and we'll have to figure out where the functions are, the intervals where the functions are concave up and concave down. Okay, so let's look at this example here. We have, for this function, find the first and second derivatives and determine the intervals where it is concave up and down. So let's do a derivative. So g prime here is equal to derivative of negative x squared plus 3x plus 4. So that's equal to negative 2x plus 3, right? The derivative of 4 is 0. So the second derivative is equal to the derivative of that, so negative 2x plus 3. So that's equal to negative 2, right? Because the derivative of x is 1 and derivative of 3 is 0. So what can we say? Well, this is less than 0 no matter what x is. So for all x in the line from negative infinity to plus infinity. So that means the g, so where is it concave up and where is it concave down? So g is concave up. So is it concave up anywhere? Well, it's not, because concave up, it means that the second derivative is positive. So this interval doesn't exist. So it's concave up nowhere. So I think in some of your homeworks it says find the interval, so the interval doesn't exist. So the answer in that case would be does not exist. Okay, and G is concave up, concave down, in the whole interval negative infinity to infinity. Okay, so those are my intervals where the function is concave up or concave down. Any questions? In this case, it was very easy. In fact, whenever you have a polynomial of second degree, so quadratic function, it's always a parabola, so it looks either concave up or it looks concave down. It doesn't have so one of the two things happens. So that means one of this interval has to be, well, doesn't exist. Okay. So okay. So next, let's do this one. This is a little more interesting. So for the function, again, we need to find first and second derivatives and determine the interval where it is concave up or concave down. So let's do derivative again. So f prime is 3x to the 4 minus 6x to the 3 plus x minus 8. So the derivative of that is 3 times 4x to the third minus 6 times x to power times 3x squared plus 1, and then I have minus 0, so I'm not going to write that down. So the whole thing becomes then 12 x to power 3 minus 18x squared plus 1. Okay, so now let's do the second derivative. That's going to be the derivative of the first derivative, which is 12x to the 3 minus 18x squared plus 1. Okay, so that's equal to 12 times 3x squared minus 18 2x plus 0, right? So that's equal to, well, let's see. So 12 times 3 is 36 x squared minus 18 times 2 is 36 again. Okay, so I can factor some things out because I need to figure out where the second derivative is positive or negative. So I want to simplify the answer. So this is going to be equal to 36x, right? And if I factor it out, so 36x from this one here, it's going to give me 1. And from here, well, I have here x squared, so that one of the x's factors out and another one stays inside the parentheses. So I can write x minus 1. So that's my second derivative. So let me write it again. I have here the second derivative f double prime x is equal to 36x times x minus 1. Okay, so that's my second derivative. So to determine where this is positive or negative, which is the same thing as saying where it's concave up and concave down, we're going to draw the number line again. So let's draw the number line and mark the points. So where this is 0, so where is this expression here 0? Well, if I plug x equals 0 or x equals 1, the expression becomes 0, so the roots are 0 and 1. And again, I have now here 3 intervals, right? Okay, so let's write down here that this is where the second derivative is positive or negative. So again, just like in the case when we were figuring out where the function is increasing or decreasing, what we do is we pick points in these intervals and then determine the sign at those points. So let's do that. So and let's start from the right again. So for x, for interval 1 through infinity, let's pick x equals 2, right? So if I do that, then I get f double prime of 2, which is equal to 36 times 2 times 2 minus 1. Well, that's positive. So the second derivative is positive in all of this interval here. So similarly for the interval 0 to 1, pick, what can I pick? I can pick the point 1/2, right? So 0.5. Then the second derivative at that point 0.5 is 36 times 0.5 times 0.5 minus 1. Okay, now what do I have? I have this thing here that's positive, right? So everything depends on this, and that's a negative number. It's negative 0.5, so the whole thing is negative. Okay? So I can write that in this interval from 0 to 1, the second derivative is negative. And similarly for negative infinity to 0, we're going to pick any number, so I'm just going to pick x equals negative 1. So I have that the second derivative at negative 1 is 36 times 0.5 times negative 1 minus 1. Actually, sorry, I did a mistake here. This was supposed to be times negative 1, right? My function is here, right? 36x times x minus 1, so 36 times negative 1 times negative 1 minus 1. So I have a negative number here times a negative number here, right? This is negative 2, so it's negative negative, so I get a positive number. So this is greater than 0. So I'm going to get that this is a positive here. So that means what? That means my function, the second derivative, is positive in the interval negative infinity to 0 and 1 to infinity, and the second derivative is negative in the interval 0, 1. So what does that mean? That means that f is so that means that f is concave down in this interval 0 to 1, and f is concave up in the places where the second derivative is positive. So that means in the interval negative infinity to 0 and 1 to infinity. Okay, so that was what we wanted to do. We wanted to find, so it's concave up, concave down in 0, 1, and concave up in negative infinity to 0 and 1 to infinity. Okay, are there any questions? Okay, so let's do this one here. So the next one is very similar. We're going to do the same thing. So again, for this function, we have to find the first and second derivatives, and then find out where the second derivative is positive or negative. So let's do the first derivative first. So f prime is equal to the, well, it's a fraction, so I'm going to use the quotient rule. So the denominator squared times the top prime, so it's x prime times 1 plus x squared minus x times 1 plus x squared prime. So that's equal to, so x prime is 1, so I get 1 plus x squared minus x times, and the derivative of 1 plus x squared is just 2x. So I get 1 plus x squared squared. And so on the top, I get 1 minus, let's do 1 plus x squared minus 2x squared. So the whole thing is 1 minus x squared in the numerator. Okay, so that's the first derivative. So let's do the second derivative. So f prime double prime x is the derivative of 1 minus x squared divided by 1 plus x squared squared, right? So again, this is a fraction, so I have to use the quotient rule. So let's do that. Again, I have to have the denominator squared, so it's going to be 1 plus x squared squared, and again squared. So that's going to be, instead of square, I'm going to get the fourth power, but I'll do that next. So I'll just do squared again. And then I'm going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, 1 plus x squared squared prime. Okay, so let's simplify this a little. So this is going to be, on the top I'm going to get 1 plus x squared prime is just 2x times 1 plus x squared squared minus 1 minus x squared. Okay, so now we have the derivative of this expression here. Okay, so it's 1 plus x squared squared. Okay, so what's that? So it's a composite function. Inside I have 1 plus x squared, outside I have x squared. So the whole thing is going to be like the derivative of x squared, right? So it's going to be 2 times the inside. But then I have to multiply by the derivative of the inside. So that's going to be 1 plus x squared prime. Okay, so then I have to divide by the same expression as before. So it's going to be 1 plus x squared to power 2 and then square that. So that's going to be to power 4. Okay, so this 4 comes from the fact that I have 2 and 2 there, so that when I take a power of a power, the powers multiply. So let's simplify the numerator because we have to figure out where this expression is positive or negative. So let's do that. So it's going to be equal to, so I have 2x times 1 plus x squared squared minus, okay, so I have 1 minus x squared times 2 1 plus x squared times, and the derivative of this expression here is just 2x, so times 2x. Okay, okay, so that's what we get. I'm just going to move this a little bit so that I have more space. So now let's look at this expression. I'm going to simplify this. So that means I'm going to factor out some of the things which are common. So let's see what's common. So I'm not going to worry about the denominator for the moment. So let's factor out what's in the numerator. What are the common terms? So there is a 2x here and then 2x here. So I can factor them out. So I'm gonna write 2x And then, okay, so what else is common? Well, let's look. Here I have 1 plus x squared, and then I have two of those here because of this power 2. So I have 1 plus x squared in both of them, so I can factor that out. So I'm going to get 1 plus x squared, right? Okay, so that's the whole only thing I can factor out. So in the first term, if I factor out 2x 1 plus x squared, then what's remaining? Well, remaining is one of these 1 plus x squares, so I can write 1 plus x squared. Okay, now in the second term, what did I factor out? I factor out this, and I factor out that. So the remaining term is this one here, 1 minus x squared times 2. So I'm just going to write that down. So minus 1 minus x squared times 2. And in the new denominator, I have 1 plus x squared to the power 4. Okay? So let's simplify this a little bit again. So this part here, there is nothing to simplify. I'm going to simplify only this part here. So that's going to be, let's write that down. That's going to be 2x times 1 plus x squared times, I have 1 plus x squared minus, and here I have this thing here, I'm gonna multiply the 2 throughout, so I'm gonna get minus 2 and then plus, because of this and these minuses, plus 2x squared minus 2 plus 2x squared. Okay, so so that's my expression, and so I can simplify it a little bit here. Well, the denominator stays the same. If I simplify here this last part, I can simplify it, right? So it's going to be, what is that? So I'm going to write it with this. So this thing here is what? 1 minus 2, so it's going to be negative 1 plus 3x squared. Okay, so the whole answer is going to be 2x times 1 plus x squared times, let's write it as 3x squared minus 1. So that's my second derivative. Okay, so that's my second derivative. Now note here, a lot of things, actually I can simplify it further because I can cancel some things. See, this part here is the same as 1 plus x squared here, so this cancels out. So so I can write this, cancel this with 3 to one of them, and I get a 3 here instead of 4. So the answer in reality is, let me write it here, the second derivative f double prime x is 2x times 3x squared minus 1 divided by 1 plus x squared to power 3. Okay, So that's my second derivative. And I have to find out where this is positive or negative. Let me do it on a separate page. So okay, so where is this thing here, positive or negative? Well, look at the denominator here. What can we say about the denominator? Well, the denominator is 1 plus a square. Well, this is always greater than 0, so this thing here is always positive. So the whole denominator is always positive, okay? So that is not going to affect the sign. So let's just write it. F prime double prime x has the same sign as, well, 2 is also a positive constant, so the whole thing only depends on the sign of just this part here, as x times x times 3x squared minus 1. Okay, so all we have to do is to figure out where this expression here is positive or negative. And again, so we have to, well, for that we have to set it equal to and solve. So if I set this equal to 0 and solve, then I have two possibilities, x equals to 0 or 3x squared minus 1 is equal to 0. Well, what's that? That's the same thing as saying that 3x squared is equal to 1. Yeah, I moved 1 to the other side. Or if I divide both sides by 3, that's the same thing as saying x squared is equal to 1/3. But that's the same thing as saying that x is equal to the square root of 1/3. Plus or minus, right? So those are the two things. So those are my roots. My roots are x equals 0 or x equals plus or minus 1 over root 3. 1 over root 3. So if I do the number line now, I'm going to get this. So I'm going to get three numbers. 0, root 1 over 3, and negative root 1 over 3. Okay? And as usual, we have to pick numbers to figure out where this thing is positive or negative. So we have now how many intervals? We have this, that, that, and that. So we have 4 intervals here. We have to pick numbers to figure out whether the function is positive or negative in each of those things. And which function are we looking at? This is the second derivative, but I mean, it's not the second derivative, it's the part of the second derivative which matters. So this is this function here as above. So this is x 3x squared minus 1. Okay, and now I'm going to pick some numbers. So what are the numbers here? So if you pick numbers like, for instance, so from 1 over root 3 to infinity, pick let's do x equals 1, right? So if I do that, I'm gonna get 1 times 3 times 1 squared minus 1. So that's a positive number, right? It's equal to 2, but it's a positive number. So I have a positive sign there. Okay. Next, I need to do from 1 over root 3 is actually 0 to 1 over root 3. Okay, so I need to pick a number which is less than 1 over root 3. So actually it's easy to see that 1/2 is smaller, right? So I can pick 1/2. So pick, why is 1/2 smaller? Because I have 1/2, right? Because 1/2, I want to show it's less than 1 over square root 3. Because, well, if you square both sides, you're going to get, well, if you cross multiply, you're going to get root 3 is less than 2, and you can just check that that's really the case. Okay, so if you do that, then you're going to get x equals 1/2. So you're going to plug 1/2 here. So you're going to get 1/2 times 3 times 1/2 square is 1/4 minus 1. So this is going to be a negative number. So I'm going to get a negative here. And then I can continue doing this, and then you will see that I'm going to get a plus here and a minus there. So it's actually, in this kind of expression, I always find whatever it is on the rightmost interval, and then I switch the signs every time I pass through a root. Okay, unless it's squared or an even power, but in these cases it doesn't happen. Okay, so I'm not going to write it down, but it's the same thing. So you pick these numbers and you get that. So what you get is that your function is concave up in these intervals, -3 root 3, -1 over root 3 to 0, and 1 over 3, root of 1 over 3 to infinity, and concave down in these intervals. Okay, so let's write that down. So f is concave up in and so it's concave up in wherever you have a plus, and f is concave down in the other intervals. So negative infinity to negative 1 over 3 root union 0 to root 1/3. Okay. Okay, so that's this problem. So as I said in the beginning of this class, I'm gonna just continue so that I finish this section. I'll do all the problems, and I will post the recording as usual. So if you have to leave at some point, you can do that, but I'll just finish this whole thing so you can look at your homework and not have a problem. Okay, does anyone have questions now so far? Okay. Um, okay, so I'm gonna continue with the next one, and before we do that, I have to say what is an inflection point. So let's I'm gonna write that down. So we say that F, so an inflection point. So let's actually do these pictures here. So let's look at this function here. So let's look at this function. So what we see in this function is we have something happening. So, well, what can we say? The function is concave up, right? So if you remember, we talked about it in the beginning. So we have a concave up here, then concave down, then concave up, and then it's up, 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 right? So there's two places on this graph where the function goes from concave up to down or from concave down to up. So that means the second derivative changes the sign, right? And that's called an inflection point. So inflection point is a point where the function changes its concavity. So let me just write it down here. So F we say that F has an inflection point at x naught, at x naught if F changes its concavity around x naught. So that means goes from concave up to concave down or from concave down to concave up. So it's the same thing as saying or if double prime changes its sign at x naught. So again, if you looked at the second derivative and you figured out the points where the second derivative went from positive to negative or negative to positive, that means that it changed its concavity, so that's an inflection point. So that's what it means to be an inflection point, okay? So F double prime changes its sign at that point. So in this example here, we have two inflection points. So let's just do, so inflection points are this one here and this one here. So this point and this point here, it's not an inflection point. See, this point here is not an inflection point because it keeps its concave up on both sides of that point. But here, so in around this other point here, it goes from concave down to concave up. While around this point here, it goes from concave down to concave up. Check. No, sorry. From concave up to concave down, right? So on all these examples that we looked at, and now what we'll show is that these examples are, so here, what is this? This is the sign of the second derivative. So it went from concave up to concave down. So that's an inflection point. And here the same thing. it went from concave down to concave up, so that's an inflection point. Similarly, in this other example, which we looked at, so we have here, we have, it went, again, this was the second derivative, so it went from concave down to concave up. Here is concave down, concave up. So that's an inflection point, that's an inflection point, and that's an inflection point. There's 3 inflection points on the graph of that function. Okay? So the next example would be find the inflection point if it exists of the following function. So let's find the derivative, second derivative, and find what are the inflection points. This is a polynomial, so it's very easy. So I'm going to do the derivative of that. So that's going to be, let me do it fast. It's 2 times 3x squared, so it's going to be 6 times x squared minus 3 times 2x, so it's going to be 6x plus 18, right? That's my derivative. And the second derivative is going to be the derivative of this expression here. So it's going to be 6 times 2x. So that's going to be 12x minus 6. So that's my second derivative. So if you want, I can simplify and write that this is equal to 6 times 2x minus 1. If I solve this and set this equal to 0, I'm going to see that the roots, so this is equal to 0, that's the same thing as saying that 2x minus 1 is equal to 0, which is the same thing as saying if I solve, I'm going to get x equals to 1/2. So, or if you want, 2x equals 1, or dividing both sides by 2, I get x equals 1/2. So, and then if I do the number line and plot the derivative of the second derivative, right? So I have 2 intervals. So at this point, this is the point 1/2, and I can see that if I pick a number greater than 1/2, so for instance, let's take x equals 1, right? If I do a g double prime of 1, that's going to be 6 times 2 times 1 minus 1, so that's positive. So this is positive, and similarly you can see that g double prime of negative 1, 6 times 2 times negative 1 minus 1 is negative. So you have that the function is changing its sign, so from negative to positive, and so that means that 1/2 is an x equals 1/2 is an inflection point. Okay. Okay. So the next examples are oh, okay, so it's the same thing here. Let me skip this problem because it's done very similarly, or all right, so we have to find out where the second derivative is equal to 0 and find the places where it changes the sign. So it's done very similarly to the previous problem. Okay, so problem 8. So we have to find something similar to what we did last time, not today. So we have to figure out where the function has a local maximum or a local minimum. So how do we do that? So let's look at the picture here. So let me draw a picture. All right, so imagine this is my function. Okay, so at this point here, I have a local maximum, so the slope is 0. And here, I have a local minimum, so again, slope is 0, right? So, but in terms of the first derivative, we can't really say whether it's a local maximum or minimum, but by looking at the derivative at that one point. We have to look around that point, because if you look around that point, you will see that, well, if it's increasing, then decreasing, meaning if the derivative goes from positive to negative, then it's a maximum. But at that particular point, the derivative is 0, so it doesn't tell us whether it's a local maximum or local minimum. On the other hand, if we look at the second derivative, it does tell us something. What does the second derivative tell us? It tells us whether the function is concave up or concave down. And note that if I have a local maximum, that means the curve has to look like this, so it has to bend down around that there. So that means the second derivative at that particular point is actually negative, so it bends down. Similarly, at this point here, I have a curve that's bending up. So at the local minimum, I have that the second derivative is positive. So there is a small chart that um, I can draw for you. So if you want to have that second, so if you want that the function looks like this, right? So that means the function is concave up. That means that actually the second derivative is positive. So there is the second derivative is positive. And if you look at something which looks like this, right? So that means the second derivative is negative. So I have the second derivative is like that. So if you want something that concave up, that means the second derivative is positive. That means at that point I have a local minimum. So this is concave up, concave down, right? This is concave down. Right? So and concave up means that I have a local minimum, right? So at this point here, I have a local minimum. And here I have a local maximum. So if I find the derivative, the second derivative at the critical point, and it's positive, that means you have a local minimum. If it's negative, you have a maximum. So let's do it in this example. So it's a very simple function. So let's find the second derivative. So I have gx, g prime x is equal to the derivative of x to the power 3 minus 6x. So it's equal to 3 times x squared minus 6. Now let's find the second derivative, right? So I have the second derivative is equal to 3 times 3x squared minus 6, and the derivative of that is 3 times 2x, so that's just 6x. Okay, so what are the places where I have a local maximum or minimum? Those are the places where my derivative is equal to 0, so I have to look at the zeros of that, x squared minus 2, and I have to set it equal to 0. If I do that, then I have to solve. I get x squared minus 2 is equal to 0. And if I solve, I'm going to get x squared is equal to 2, which is the same thing as saying that x equals plus or minus square root 2. So those are my roots, right? So those are my roots of the derivative. So those are the places where I have a local maximum or a local minimum. So let's do this is minus square root 2, and this is plus square root 2. Okay? And so now I want to figure out whether this or this is a maximum or a minimum. What do I have to do? I have to plug these values into the second derivative. So now if g double prime of square root 2 is equal to 6 times, right? So this is 6x, right? So it's equal 6 times square root 2. So it's a positive number. So that means there is a maximum or a minimum. If the second derivative is positive, right? If the second derivative is positive, that means I have a local minimum, right? So local minimum minimum. If you have the second derivative is negative, that's x times negative root 2. That's negative. So I have a local maximum. Okay? So again, you have a local maximum, that means the second derivative is negative, and local minimum, that means the second derivative positive. This is called the second derivative test. So I'm going to write it again here. So we have local minimum so local minimum is the same thing as saying the second derivative is positive. Okay, like in this situation here. And local maximum, that means that the second derivative is negative. Okay, at that particular point, just like in this example here. Okay, so so that's what we did. We figured out that there is a local minimum at the square at root 2 and local maximum at root negative 2. Okay, negative root 2. Okay, so let's see what's the next problem. So for this function, find the first and second derivatives and use the second derivative test to find the local maximum or minimum. So it's the same thing, but the calculation is a little different. So let's do it again. So here I have that the first derivative is equal to the derivative of 2t plus 3 over t. So that's equal to 2 plus 3 divided by, well, it's 3 times, so it's t to power negative 1, right? So let's remember what's the derivative of that. So it's 2 plus 3 times negative 1 times t to power negative 2. Okay, so that's the first derivative. So if I write it out, it's going to be 2 minus 3 divided by t squared. Okay, so I need to set this equal to 0 to find the critical points. Okay, so So I want to say f prime t equals 0, right? So that's equal to 2 minus 3 over t squared is equal to 0. Well, I want to simplify, or actually let's right, let's yeah, set it equal to 0. That's the same thing as saying that 2 is equal to 3 over t squared, which is the same thing as saying that if I cross multiply, I'm going to get t squared is equal to 3 over 2, right? So if I cross multiply t here, I'll get t squared there, and then I take 2 and take it down, I'll have 3 over 2. So then I will have that that's equivalent to saying that t is equal to plus or minus root 3 over 2. Okay, so we got that. Now we have to figure out whether at each point the derivative, the second derivative, is positive or negative, because we want to find out whether we have local maximum or a minimum. So let's do second derivative. Well, the second derivative is the derivative of 2 minus 3 over t squared. So that's equal to what? That's equal to derivative of 2 is 0 minus, and then I have the derivative of 3 over t squared, so it's going to be 3 times, and the derivative of t squared, 1 over t squared, that's the same thing as the derivative of t to the power negative 2, so it's negative 3 times negative 2 times t to the power negative 2 minus 1, right? Which is the same thing as 6 times t to the power negative 3. Okay? So that's my second derivative. Okay? So where is it positive or negative? Well, it's positive if t is positive, if negative if t is negative, right? Because what is this? This is just 6 divided by t to the power 3, right? So if t is positive, then the third power of t is positive. If t is negative, well, the third power is squared times the first power. So it's the same power as t itself. So if t is negative, then t to the power 3 is negative as well. So that means f double prime t is positive for t positive, and it's negative for t negative. Okay, so that means what? If I plug, so I have two numbers here, right? I have this plus and minus root 3 over 2. So that means what? That means if I have f double prime of the positive root 3 over 2, that's going to be positive. And the negative root 3 over 2, it's going to be negative. So what does that mean in regards to the maximum and minimum? Well, if the second derivative is positive, that means I have a local minimum at that point. And this one is, if it's negative at that point, then I have a local maximum. Okay? So I have a local maximum and local minimum. So it is possible to find, so let's see, to find the local maximum and minimum. So it's possible that in your problems on WebAssign, the answer would have to be in terms of first and second coordinates. So if this is, so if you, in the maximum, you have to write that x is equal to negative root 3 over 2, and then to find y, you have to plug that into f, right? So you have to plug negative root 3 over 2 or whatever number you get for your problem inside of f, inside of t here, okay? So that would give you a pair of points. This would be x, and then f of that x would be your y. Similarly for the minimum. I just found the x's, okay? Okay, so and final problem is this. Okay, so um, the so problem 10, flight of a rocket. The altitude in feet of a rocket t seconds into the flight is given by this formula here. So we need to find the point of inflection of this function. So what is the maximum velocity attained by the rocket? So we need to find the point of inflection of this function, and what is the maximum velocity attained by that rocket. Okay, so so let's do this problem. So let's find the inflection point. For this, we need to find the derivative and the second derivative. So let's find the derivative. So f prime is equal to the derivative of this expression, and it's equal to negative 3t squared plus 54 times 2t plus 480. Okay, and so the second derivative is going to be given by negative 3t squared plus 54 times 2t plus 480 prime. So that's equal to negative 3 times 2t plus 54 times 2, which is 108, times the derivative of t is 1. So the whole thing is negative 6t plus 108. That would be my second derivative. So let's find where it's concave up and concave down. So let's look at the number line. So where is this equal to 0? So if I set this equal to 0, I'm going to get that negative 6t plus, well, is equal to negative 108. So t is equal to negative 108 divided by negative 6, right? So if you calculate, that's going to be 18. So if I draw the number line and mark the point 18, then I'll have to figure out where the function is positive and negative. Well, it's actually very easy to see that the function is going to be positive here and negative here. And it's easy to see because it's a linear function, and the slope of the linear function is negative, so it has to be a decreasing function. So it has to be bigger on the left and small on the right. Okay. So, or you can just pick some points and see that it's indeed the case. Okay, so so that means that the function changes its concavity from that side to that side. So that means at this point here we have an inflection point. Okay, so what is the maximum velocity attained by the rocket? That means we have to figure out where the derivative is the biggest. So, well, let's look at this picture here. What is this? This is the picture of the derivative. Well, that's the second derivative. It's positive and negative, but what is the meaning that the second derivative is positive? That means that the first derivative is increasing, right? So this means that f prime is increasing for x less than 18 and decreasing for x greater than 18. What does that mean? If a function is increasing for numbers less than 18 and decreasing for numbers greater than 18, that means at 18 it has a maximum, right? So that means f prime has a maximum at t equals 18, right? So the question was, what is the maximum velocity attained by the rocket? So all you need to do is you need to calculate the derivative at 18, right? So at that inflection point, you have to calculate the derivative. So if you calculate the derivative, and just write f prime of 18, just plug 18 into this expression here, you will have your maximum velocity. Is the maximum velocity. Okay, so this is the end of this class, and so we covered the whole section 4.2.